Hashing is a fundamental technique in computer science in general, but also in data management. So just in data management, there are many applications. For instance, there is checksumming to find out whether the contents of a page, for example, is correct or not. We talked about that in the context of storage management. On hard disks, you have that. So hard disks use that, but also file systems use that. File systems use that to find out whether the stuff that was written corresponds to the stuff that is read. Checksumming. Duplicate detection, that's a very important application of hashing as well, to find out whether you have an entry already. So for instance, we looked at that in the context of shadow storage, and then I told you how to extend shadow storage to also merge physical contents, and you can detect duplicates, duplicate physical pages using hashing. That is one application for that. Similarity search, you can also use hashing to find similar entries. There are a zillion different ways of doing that. So one prominent example to find similar entries, similar data items using hashing is called LSH, which means locality sensitive hashing. That's another application of hashing in the context of data management. Well, then there's all this encryption and signatures, of course. So many of those algorithms are basically based on hash functions, special hash functions. If you think about these SHA functions or the MD5, all these functions are basically hash functions. So pseudo-randomization, that's another thing where we needed to generate random numbers. And as you probably already know, current computers can't generate random numbers. All these numbers are just pseudo numbers. So basically what a pseudo random generator does is it starts with a seed. It has a seed value. Let's set it to 42, whatever. And based on this seed value, it generates a sequence of numbers. And those numbers follow a specific distribution. But basically what these random number generators do is they use a hash function internally to come up with the next seed. So that's another application of hash functions. These hashing functions and hash tables and hash maps, and we will look at that in a moment in more detail, all of these are building blocks for query processing and data management. So they are used all over the place and very important. There are two types of queries we really have to differentiate here. So one type of query that's important is a point query. That's a query asking for a specific key. So if you have a key and ask for something like all the tuples where the ID equals 42, then this is a point query. In contrast, in a range query, if you ask for something like, let's say, all the IDs that are in a specific range, let's say, whatever, 7,000. So here you get a range of values. That's called a range query. In general, it's fair to assume that a standard hash function supports point queries very well, but hashing typically doesn't support range queries very well. Well, that is not always true because it depends a lot on the specific method. So in general, this is true. In general, hashing works well for point queries, but not for range queries. However, you can also create methods that also work pretty well for range queries. But in the following, we will start with point queries. Okay, so there are other applications, but I think those are the most important ones. So let's start with point queries. What is a point query? Let's define it briefly. So given an integer domain from 0 to n-1, so n different values, n different integers, n is potentially large, and you have point queries asking for data items having a specific key in that domain. So for example, what is the address of the student having this ID? This is 424,342. And then the question is, how do you support this by an index? A naive solution would be to use an array. So if you know this n, basically what you can do is you create an array. Basically what you do is you do something like this. You say you want to have an array of data items. Let's call it array. And then you say whatever, new data item of size n. Okay, That's it. And depending on the programming language, this might mean that basically this is an array of pointers to actual data item instances, or this is actually already the data. So let's assume we have pointers. So basically this is an array of pointers. Each slot points to a specific data item. Then this boils down to having entries where most of the entries are set to null and only some of them point to the actual data items. So in the extreme case, as visualized here on this slide, you see there's only this item here. One slot points to something. This points to this data item. Everything else is set to null. And this has obvious drawbacks, of course, because usually the programming, it depends a lot on the operating system and the programming language. But what usually happens in this kind of situation is, depending on how much size you reserve for a specific slot, let's assume it's just 64 bits, let's say it's just 8 bytes per entry, then you basically have something like 8 bytes times n or something, which is a storage space that's being allocated by just calling new array. However, there are twists. Actually, if you're running on Linux and then virtual memory management kicks in, you may actually create very large arrays, but then those arrays are not created physically. They are only reserved virtually. Basically, virtual memory management kicks in and then reserves a specific range. So if you're unsure about virtual memory management, look back at my video on that. But basically what may happen when creating a large array is something as the following. You basically, so if this is the array you create, and let's assume this is whatever, you create 1 terabyte, let's say that is 1 terabyte. This doesn't necessarily imply that the 1 terabyte memory is allocated. So this only implies that the memory region is reserved for that specific array. Only when you try to write to specific addresses, then the physical pages behind the virtual pages are actually allocated. So this is again a nice example of virtual memory management. Only if you touch something, only if you actually write to a virtual page, the physical page gets allocated. So it wouldn't be fair to say that in all cases, when you reserve an array like that, the memory is also physically allocated. It really depends on the operating system, how smart the operating system operates under the hood. Okay, but anyway, in the worst case, what may happen is you allocate something like that and then a lot of memory gets allocated. So, and that might be really something. If this is in the order of millions and billions, whatever, you might be allocating gigabytes or terabytes of data. And that's maybe not so great, just to have an index on those data items. Well, and if you look at that, how is that index, how is that array implemented? It's super trivial. So basically, an insert method is like you have this integer that you want to use as a key. Here I use this, if you go back, so I have data items and I use this ID attribute as a key. So you have an insert method and it takes a key and the value, basically assigns the value to this specific slot in the array. Yeah, that's all that happens. And of course there are many method names for that. So I call it the insert method, but this is also called a put method or the set method. And then delete is very similar. You just need to specify the key. So you basically set this to null or whatever the type represents, whatever you use to represent that this slot is empty. That might depend on the type a little bit, but that is what you do if you have an array of pointers, of course. And this is then also called the remove method. And the third method is what I call the point query. So what this says is I want to have all the entries from the array with that specific key. So basically you return the slot that has that key. And of course this is also sometimes called the get method. So space usage, as I explained already, that might be tremendous. This might lead to problems. So basically all of these slots, not just the ones I depicted here, all of these slots point to null except this single item that actually has a real pointer to some data item. And this is not the best in terms of space usage, obviously. Yeah, it's really easy to calculate if you have like, assume n is like, let's say 100 million. 100 million is the domain, the size of the domain, so values from 0 to 100 million minus 1. So let's assume you have your data set only has, let's say, whatever, 10,000. You have 10,000 different tuples you want to index, so something like that. And then you can easily calculate the average occupancy of that array. Of course, you just divide n by x, and divided by x is 10,000 again, right? So 1 out of 10,000 slots is actually occupied. So this is not a good use of resources, of course. And that's what we want to avoid. So it's kind of straightforward to get to the idea of static hashing. What is static hashing doing? So rather than allocating an array of size n, it says, okay, let's allocate something that's smaller, m, that's really substantially smaller typically than n. We allocate an array of size m only, but then what we do is we transform the incoming key from this original key space, from 0 to n minus 1, that was the original key space, we transform that to this smaller range from 0 to m minus 1. So basically, whenever a key comes in, whenever from the outside we talk about a specific key in this range, we have to translate it to that range. That is what hashing is about. So how do we translate that? And this is achieved by the so-called hash function h, which takes a key and returns a hash. So here we can discuss whether the hash that's being returned is already reduced to that range. So it depends on which textbook you look at. You could also say the hash function gives you a value in a very large range, which may still be larger than this range. In that case, you still have to do something like modulo the size of the domain, so that's m. And then you get the actual slot in that array. So it depends on how you define your hash function, but you can also define this modulo m directly inside the hash function if you want. So let's look at an example. So we have our domain from 0 to n minus 1. We have those slots. But now, rather than allocating this array, I only create this one. That is the array being created. And now, whenever I talk about a slot that has a specific key in this domain, I need to translate it to this smaller domain. And I do that with the hash function. So basically, the hash function takes this key with respect to this domain and translates it to a key in the other domain. That is what the hash function is doing. The hash function implements this mapping, this arrow here from the bigger domain to the smaller domain. So when I want to insert something into the hash map, what I do is I compute the hash function on the key. I receive this number 77, and that is a bucket I use in the array. And then I basically set the pointer in this slot to point to this data item I want to insert. So in this example, I actually assume that I insert a specific data item, and I use this attribute ID as a key in the hash map. So as with any index, those indexes materialize a mapping from a key to a value. Key maps to a value. And I say here, the key I use is this ID column in this concrete example, and this maps to the data item. That is what the example shows. But of course, you can define keys and values as you wish. For the moment, I assume that the type of the key is some integer. Okay, so that is what happens, and then you can insert more elements if you want. Here's another data item with this ID, which is pretty large, 3 million something. This might translate to slot number 6, so you insert it here. So slot and bucket means the same thing here. So I call it slot here in the array. Here in the hash table, it's typically called bucket, but it's the same thing. It's just smaller. So let's look at the methods. Let's look at the methods of such a hash table or a hash map. So here, what we see is the only thing that changes over the array is that before setting the specific array slot, we call this hash function. So we don't use key as the index into the array. We use the return value of the hash function as the index in the array. So that's the only thing that changes over the array. And that changes in all methods, of course. When you want to delete something, you first call the hash function on the key, and whatever is the result is used as the index in the array, and so forth. So that is how a hash map functions, basically. And one thing to note here is, of course, this doesn't have to be an integer domain in the hash function. So those hash functions can be defined on any key type. That's what I'm displaying here. So there's no need to have an integer type here. This may be any type as long as I can come up with a decent hash function that maps this key type to my domain that I use in the array. So for instance, hash functions can also be defined on strings. So what I'm saying is I have this key value mapping now, and before it was only an integer. Now I say whatever, the key type can also be string. And I map it to, I want to map this to data items as before. Okay. So but what's the type of the hash function? Well, the hash function, of course, maps from string to an integer still. That's unchanged because I need this as an index into the array. What I use as a value then in the actual array used by the hash map is a different story. That is defined here by the v, by the data item I'm using here. So this is a data item in this example, but the hash function always maps to some integer, maps whatever input type to some integer. One problem, of course, which is likely to happen in hash maps are so-called collisions. What might happen is you have two different keys with respect to this domain here, domain 0 to n-1. So we have a key, we have this key and we have that key. And now it might happen that the hash value of both of those keys is actually the same. So whether you hash this key or whether you hash that key, both will have the same result, 77. 77, okay, which would mean that both need to be inserted into the same bucket. And this is called a collision, meaning you have two keys in this domain that map to the same bucket in this domain. And of course, as we have this very big domain and this smaller domain, these collisions must happen eventually. They must happen at least in those cases if you have one more entry here, then you have buckets here. Then there must be a collision, that's clear. So we must handle that somehow. Again, this has nothing to do with whether the attribute you use here is a key in the original table. So if this is a primary key, let's assume, like this ID we had here, primary key implies no duplicates, right? No duplicates, this is impossible, otherwise we wouldn't be allowed to call this a primary key. Here we have duplicates, but the duplicates are with respect to the return value of the hash function, of course. So even if that's a primary key, that's a primary key, we have duplicates in that space, of course, and we must handle that. So how do we handle that? Well, one possible way of handling that is to create chains, overflow chains, which means if there are multiple values that map to the same bucket, you just append them in a list. So here you don't have buckets pointing to individual items anymore. You have buckets pointing to lists of items. And then you should change your implementation accordingly to be able to handle that. So if you go back to this method here, where I said, okay, I have an insert operation, and whatever comes in, I hash it and assign that bucket to be that value. Well, here you could lose information, of course. If the first entry sets this to, let's do it here. Yeah, if the first entry does the operation array 77, yeah, sets this to point to this one, and then I would have another insert operation that also goes there and sets this to point to this one. When calling this operation then, I would of course lose the information that this data item is also mapped to this bucket 77. So you should change your implementation accordingly to make sure that you don't lose any of the data items once there is a collision. So that's a very common implementation, to not point to buckets of items, but to point to buckets of lists of items. That's one way of handling this problem of collisions. There are many other ways, and we will look at that in follow-up videos. So one design goal we will talk about in the following videos is also the hash function has an impact on the number of collisions. So you should choose your hash function in a way that whatever items you insert here, they're evenly distributed over the different buckets. They're uniformly distributed over the different buckets. And that is actually the core idea of the naming of a hash map. So hash in English at least means to split, to partition, to cut into pieces, which is kind of not the perfect naming here. There's a better name for that in German. In German, so sorry for using a German word for that, but in German this is called eine Streutabelle. Streutabelle. This is German term for that. And Streutabelle means a slightly different thing. This basically translates to distribution table or decluster table. So this prefix here of this word implies that the values that are hashed are distributed over the different buckets. That is the core idea of hashing. So the English term hashing focuses a lot on to partition the stuff. But that's not the core idea. To partition the data is not the core idea here. The core idea of a hash table is actually to decluster, to distribute evenly over the different buckets. That's a very important property of those hash functions. We'll look at that in a moment. So the better the hash function, the better the hash function is in declustering, in distributing the data items over the different buckets, the lower the number of collisions. That's what you want to have. You want to lower the number of collisions. So you could think about an extreme case. If you really have a super bad hash function that translates from this original domain, so this domain from 0 to n, to this one in a way that whatever key you have here, it's all mapped to the same slot. Yeah, that would be the extreme situation. Whatever happens, it's all mapped to the same slot. That's really the worst case for a hash function. So basically, it's a hash function that says whatever key comes in, this is 42, the slot is 42, okay? Then, of course, you end up with a list. So basically here in that bucket, you would end up with a long list of the entries, and then you wouldn't gain anything in point queries, of course, because then you still have to go through that list of data items. A good hash function does a different thing. A good hash function, whatever happens here, whatever keys are inserted, they're evenly distributed over that specific space. And that's very, very important. So that's a bad hash. We will look at some more examples of that when talking about how to design those hash functions and when talking about the different problems that may occur in picking the right hash function. Anyway, what may happen in this, we have to pick this size of the array wisely. In implementations of those hash maps, you should be aware that eventually it might happen. So even if you have a very good hash function, it might still happen that each bucket is occupied and maybe even each bucket points to a long list of items. In other words, this array is too small. In those situations, you have to expand it, you have to grow it, which boils down to rehashing all of the values. That is an important operation. So if the occupancy, if the number of elements in the hash table is too high, according to the specific size, you have to pick another bigger array. Basically, then you create a new hash table with this larger value, and you reinsert all the entries from the old hash table into this new hash table, and that is called rehash. This operation is called the rehash. Each and every entry has to be rehashed with respect to the new m prime used for that bucket array. So to sum up, hashing is a very important technique to support at least point queries very well, very effectively. What hashing does is it maps a large key space to a way smaller key space that can be represented by a small array of buckets. You should be aware to handle those collisions, and you should avoid that the lists you're pointing to in overflow chains, so if you're in this situation, the chains shouldn't get too long because otherwise you lose on search performance. So if you want to express this with O notation, of course, a hash table for all of these operations. If there are no collisions, a hash table has O1 in all of these operations. All of this is O1. This is O1. This is O1. And this is O1. Okay. If you don't have any collisions, if you get more collisions, it might happen that a point query finds a specific bucket that is still O1, but then inside the bucket you find a long chain of those entries. That's what we saw here. So here it's O1, of course, to get to that specific bucket, but then this might be a long bucket, and then depending on the size of the lists, the number of elements in the list, you obtain the search complexity in terms of O notation. So be careful to not end up with these long lists. If you liked this video, don't forget to hit the like button. Thank you. So if you want to see more database videos, be it in English or in German, take a look at my website datenbankenlernen.de. It has a couple of English and German videos. You can also subscribe to my YouTube channel, Jens did, or you look at our website infosys.uni-saarland.de. See you there!